Good day, my name is Edmund and welcome to my talk on estimating windstorm losses using Mathematica. Okay, well, good morning, everyone. Thank you for joining me. My name is Edmund Robinson and I work as a actuarial analyst with Validus Reinsurance Limited based out of Bermuda. Today I'm just going to go over a interactive workflow on how Mathematica can be utilized to estimate windstorm losses. Generally what happens, there will be a windstorm, and in this case we're going to look at a hurricane. Things will happen on the ground, and at that time insurers and reinsurers, those being insurers that insure insurers, then want to sort of get information on what has happened, how much damage has occurred, and so they can start making moves to set aside funds to address the claims that are eventually going to come in. So a bit about my background. I spent some time in financial industry doing portfolio attribution analytics, and then recently switched over to the reinsurance industry where I did risk management analytics for emerging risk, and now I'm moving into actuarial analysis with, in particular, actuarial pricing. So one of the reasons, before we get too deep into it, one of the things that I like about using the Wolfram language is that it puts at your fingertips many knowledge domains, and you don't really have to go out to search to learn how to use. Well, you don't have to go out to search to find packages or products to allow you to access those domains, because all of this information and plenty of functions are there available for you to use. And this is one example. So in this workflow, what I've listed here are just a few of the domains that this workflow covers. You can see we're going to be doing data import and navigation, geographic visualization and geodetic computation, geometric computation, and you'll have this slide. And under each one of these areas, I just give you an idea of some of the functions that are being used from those knowledge domains. Knowledge base, we're going to be doing things with entity framework and administrative divisions, probability and statistics. We'll touch on parametric and non-parametric distributions, random variates, cumulative and probability density functions. We're also going to do a bit of parallel computing, numerical computation, data visualization and presentation, and even some basic user interface construction. So all of these knowledge domains, and this is a tiny fraction of what the Wolfram language provides you, we're going to make use of in this presentation. So again, what I'm doing is presenting, we're going to be looking at third-party GIS data, and we're going to import that into Mathematica and do some manipulation and combination of that with some data so that we can estimate this potential loss from this event. Some of the interesting things that you can do, and this is from the Wolfram volume visualization, is that you can have a look at to see what exactly are the properties of a tropical cyclone or hurricane. So this link here will take you to that Wolfram visualization. I've only made one tweak to those functions, and I was just, because we're in the southern hemisphere, I just changed the equations very slightly such that the vortex would rotate counterclockwise instead of clockwise. And so we can see here wind direction and even air pressure. So it's a low pressure system in the center, and we got higher pressures on the outside. So that's just, if you've never heard or seen or know anything about a hurricane, that'll give you some information. What are the steps that we're going to go through? We're going to collect some storm GIS files. We're going to then take a look at what's inside of that file. The file type is a very data-rich file type. There's a lot of information in it, and I use a technique here that helps us to navigate that sort of data-rich file type. We're going to simulate some contract losses within the path of the storm, some contract locations within the path of the storm. We're going to simulate some losses from those contracts, and then we're going to analyze that set of information to produce that set of data to produce some information. So first things first, where can we get some storm GIS files? The U.S. National Hurricane Center has a GIS page where you can download geotiffs, shape files, and other information on current storms and on past storms. It has lots of different information in it, and also the U.S. National Weather Service also has information where you can get on sort of flash flood risks from current like inland storms ongoing, and also you can get river outlooks and other information. So if you wanted to see what that looks like or where that is, if we're on the National Hurricane Center's website, this is just their landing page. So thankfully, no activities going on right now. You can see Bermuda actually right here above the O, that little speck in the middle of the Atlantic. But if you come up here to Data and Tools, you actually have to click the Data and Tools header. You'll come to this analysis tool page. If you click this GIS data link, it'll take you here to their GIS data products. And then you can look at all the different things that they have, wind speed probabilities, potential storm surge, flood. All this information is available for you for free to download and analyze in whatever in your projects in your notebooks. Okay, so let's go and grab one of these. What we're going to use for this example is Hurricane Matthew from 2016. It actually made its way through the Caribbean and then raked itself up along the eastern side of the U.S. So I'm just going to go directly in and just grab this latest file from NOAA, and I'm just going to do a slight transformation on it. So I'm just grabbing the file name, and then I'm putting it inside of a data set, because this is a very rich file type that has lots of information in it. So let's look at some of that information. One thing that it has are the wind swaths. It also has the wind radii, as well as a lot of other data. So let me just get these running. So you can see here, it came along through the Caribbean. So this outer sort of darker purple is the area that experienced tropical storm force winds. This inner sort of dark blue is the area that experienced hurricane force, so less up from category 1 to category 2. And then this sort of light blue in the middle is the area that experienced major hurricane force, so that'll be category 3 and above. But we also have inside of this file wind radii, so that we can, if we can just position this just so, let's try doing this. We can then sort of scroll along and we can see at any particular date what that sort of wind radii forecast look like as well. And they do it in quadrants. So, again, the wind radii correspond to this wind swath. So this purple area is the area that experienced tropical force. The darker blue is the area that experienced Cat 1 to Cat 2 force. And then the light blue is the area that experienced major, so Cat 3 and above force hurricane winds, force winds. So this is, if we grab that file and sort of put it into a data set, this is all the information that is in that one file. So we can see the radii, the wind swaths, the actual line, the track line, and then the points at each of the center of the storm at each particular day. And then, of course, this is navigable. What I was using above was the wind swath geometry and the radii geometry to draw all of those images on a geographic. We could take a quick look if you want. We could just expand this here, and you can have a quick look of the code that was used to do that. So the first thing I do is I just collect the synopse times here, and then in a manipulate using overlay, I overlay the radii on top of the wind swath that we created here. All right, so now we have an idea of where it went and how intense it was when it was there. Let's move into doing something with it. Now, loss models and geo-encoded data in the industry are highly coveted, so we're not going to go off and connect to any in particular databases. So the only thing we can do for this presentation is just simulate some of that information. So we know that the area that we're looking for, the area that has the most insurance penetration, is the US South Atlantic states in the area that this storm passed through. So what we can do using some of the information available to us from the Wolfram knowledge base, we can just go off and we can say, okay, find me all of the US continental US states. So that's what I'm doing to get all of these sort of gray states with the white borders. And then I can say, oh, for a particular set of states that I'm interested in, so these US South Atlantic states, get me some additional information about that so I can sort of show that differently. And so all I've done here is just brought in this information all from the Wolfram's curated data and just labeled each state with a tooltip with their name and their state flag. So we can just, we know what we're looking at and just some additional information, because I never saw state flags. I didn't realize that that US states had their own flags. So what we can do now, since we know that this is the area that we want to work with for our simulation, for our presentation, what I'm going to do now is simulate 5,000 contract locations within these states. Now, if you were in some of the talks early in the week, this is going to be a lot easier to do in the coming version, because they actually, Wolfram employees actually demonstrated a random geo point. So but because this is 11.3 and I don't have access to that, all I'm doing is I'm just taking the polygons from this area, converting them so that just removing the geo position tag that's in them. So then they just become points. And then I can get random points within that, and then I just convert them back to geo positions. So if we do that, and then we can plot those positions, we can see these are the 5,000 sort of home or business or skyscraper, whatever locations in the area that we're going to do our analysis in. So this is very interesting, because we're combining geodetic computation with probability and random variate generation, different disciplines that we're mixing together to create something, and it's all under one roof, all under one package, which is what I quite enjoy. So that's great. We can see all these places, which ones actually had something happen to them. So what I do next is I say, okay, well, let's go. This is the data set that we looked at earlier, and I'm just using that data set. There's a function called query that data set will sort of automatically use if you start to give it commands inside of square brackets. So I'm taking the second item, which I know is the wind swath regions, and I am sorting that by geo area because I want the smallest one first to go up. And then I'm picking out the ones with geo within Q, the contracts that lie within those wind swaths. And then as I roll back up, I take the complement. So the smallest one only has things in it that belong to it, but the next swath out will have all of its points plus the points from the smaller one. So I'm just doing the complement, folding that outwards. So I only get, so I'm going to end up with 3 sets of geo positions, one that only contains the major storm, one that only contains so the major hurricane, one that only contains the hurricane, and one that only contains the tropical storm. And then we can plot that with a bit of extra information, and then to get this plot that shows us, okay, exactly what has happened to our portfolio of contracts. So we can see here that we have just over 1,600 were exposed to tropical force winds, just over 300 were exposed to hurricane winds, and 53 were exposed to major hurricane winds. So already we have some information immediately available to us that we can start to work on. Now, that's great. We know where they were. We know what winds they experienced. Now let's figure out what does that mean for the insurer that holds those policies and the reinsurer that has reinsured those policies. So again, we're going to just simulate this because we're not going to connect to any particular IP to get this information from any particular company. So what I'm going to do then is I'm going to simulate the loss for each contract using a Pareto distribution. And in order to do that, I'm actually going to randomly generate some Pareto distributions in order to have that happen. So I'm going to use these, a Pareto type. Okay, so we'll just set up those, and I'll just show you real quick what family of distributions I'm going to use. So you can see here, this is Pareto, and all I'm going to do is varying K and gamma here. And so as I generate these things randomly, I'll be picking one of these loss distributions for each one of those contract locations. So let's just do that real quick. This is just to, you can just see that, yep, that's indeed what we're dealing with here. And we will, so again, at this point, because you know which individual contract has experienced what loss, you can then start to do things if you want to make slight adjustments to their loss function because they experienced higher wins than the others. Now that you know which individual contracts have done that, you can make those changes. Here we don't. And then this is just to show you that, yes, I have indeed done that. I'm taking the first 20 and just showing you these are all of these symbolics just waiting there to be used from the random generation. Of course, we held these two variables constant, parameters constant, and the other two we generated. So let's simulate using Monte Carlo some losses here. So what I'm going to do is simulate 100,000 events for each of around about 12,000 contracts. So it's going to be 120 million random observations that we're going to make. I'm going to do this in parallel because why would you do it in serial when it's so easy to do it in parallel? So all this does, let's just start that running. You see here it's launching. This machine can handle 4 kernels. I don't know why it's taking so long. Oh, could not provide a subkernel license. So I guess the version that this is on does not have subkernel. What version is this? This mustn't be 11.3. Well, if this was a version that allowed parallel processing, I think this must be desktop. I don't think it ran. Let's just check. Check to see if it ran. Oh, it did run, good. So we didn't get into the parallel processing, and it took about 9 seconds to run in serial. And that was both generating the 120 million random variates and also totaling 100,000, totaling them across the 100,000 simulations as well. So very fast and quick to do. So what do we want to do now? Let's just look at the 8,000th iteration over across all of our random variates. So you can see that there are definitely 1,200. You see 1197 here, and you see the other 3 on the sides. 1,200 in all, and everybody's generated nicely. All right, so we've got the data. Let's do something with it. Of course, what we would like to do is visualize what that loss, how that loss is distributed across that contract of portfolios. We can do that quite easily here. I'm just forcing it to use bin widths of 5 million. But this is a long-tailed distribution. So if we said, okay, let's see the full tail, this part here is just this tiny part here. And then you can see there's going to be some losses way out here for some larger properties or industrial type buildings or something from our simulation. Okay, that looks nice. Let's see what else we can make from that. We can create a smooth kernel distributions from that, which now we can use analytically to do some other from its properties. So first thing we want to do is just make sure this works. Is this truly a PDF? Well, yes, it integrates to 1 from 0 to infinity, as we can see here. So we're now getting into symbolics and numeric computation, and everything's just flowing through quite nicely. So let's see what that looks like. Let's do something to help people have a look at that. And we can just combine those guys together quite easily, and we now have the histogram and the smooth kernel overlaid. Okay, that's interesting. What else can we work with? What's really important to the industry we always hear this in the news, it was a 1 in 200 year event or 1 in 500 year event. What they use when that happens is they're interested in VAR, which is value at risk, and TVAR, which is total value at risk. we can calculate that from our simulations by taking the floor. We calculate the index of that return period. You take the and then you take the floor, so that'll give you the value at risk, and that same calculation, but then you're going to take from that index all the way to the end, and take the mean of that, and that'll give you the total value at risk. Okay, so we can calculate those from the simulation. Can we also do that with our density function? Well, yeah, we can. So we can see from the simulation, and we can see from the density function they're quite close. Can we do it? Can we do the t-var? What we can do now is we can actually set up statistical notation. The equation for total value at risk is exactly this, and you'll see this in all literature. It's the value at risk times the probability that x is greater than equal to is greater than the value at risk over 1 minus alpha, this being alpha, times the expected value that x minus the value at risk, given that x is greater than the value at risk. So you can put in your formulas and your information exactly how they appear in your text, so which completely removes any, it significantly reduces any chances for error, because what it is that you see and how you look at things mathematically, you can actually put that information directly into your workbooks and into your workflows. And then it's easy to calculate for more years. So this is the 1 in 50, 1 in 100, 1 in 250. And you can spruce that up a bit by adding some formatting. And then you can even go a stage further and say, well, I see you got the 150, 100, 250. I really want to see a different return period other than the ones that you've provided. How can we work that out? Well, you can add just a little bit of additional code, and now we can see that we've added that last row so that the user or whomever's looking at this report can select their own return period in addition to the standard ones if they had some interest. And then we can also do some interesting things like looking at truncated t-var, where you're not looking over from your return point to the end, but you're looking at between two return periods. And so here we're looking at the truncated t-var between the 1 in 10 and 1 in 100, and we can play along with this and look at different t-var ranges. Okay, so running quickly out of time, but we can also look at the CDF histogram of the losses. I'm just going to run all these at once and just talk about them as they come up. We can look at the cumulative density function, and then we can sort of look at this event in the context of other events. So you can see that we've had, I've put here 3 other events in the context of the loss distribution of this event, and then we can sort of analyze that in terms of a loss instead of a return period. So above we were looking at things in terms of return period. Here we're looking at things in terms of a loss. So as I vary the loss, the percentile and its return period comes up. So this event in context of event 2 in context of the current event was a 1 in 44 year event. And then we can sort of put it all together to do some sort of report. So you can use this with like create document, or you can have this deployed to the cloud, to your private cloud, or to the Wolfram cloud, and you can sort of start to get out information. So you can combine things. So I wanted to show this so you can combine things, and it's quite easy. All I've done here is taken the plot that I've done before, and I've inserted as an epilogue this interactive table. So now this table has an annotation that actually is an interactive calculation that's going on, calculating those return periods as we go. And then finally, we can throw all this together. So our geographic plot, and our other information into sort of a little dashboard. And this is, let's just make this a little smaller. Let's do this 100. Yep, into an interactive dashboard that again can be deployed. So you can look at these things in the cloud or in a CDF, enterprise CDF, or things like that. So there you have it. An interesting way, I mean, I think we've used quite a lot of technologies from different disciplines to quickly sort of get something in and push something out that that gives us information that we didn't have before. Thank you. Any questions?